Hello, welcome to webinar number 13. We're talking about pulleys today. So a pulley is an example of a simple mechanism that is designed to, well, usually increase the force. Sometimes to increase the speed, but generally we use pulleys to lift things. Before we talk about pulleys, let's talk about constraints in mechanics very briefly. So imagine you have two objects connected by a rope. So let's say we have um, a box mass M1 and a box mass M2. And imagine that there's a force pulling on the second box, some sort of force. Now, what would happen is that both boxes would accelerate because there's an unbalanced force. So both boxes would accelerate. And the acceleration of box 1 is A1, and the acceleration of box 2 is A2. But what is a constraint? Well, a constraint, because they are connected by a rope, so they can only move together, sort of. Of course, provided the string is taut, right? Because if the string is slack, anything could happen. Like M2 could stand still and M1 can travel. But assuming they are connected by a string and the string remains straight, A1 must be equal to A2. They have to have the same acceleration. And that is called a constraint. In mechanics. So we use constraints a lot when we solve problems. For example, if we have a pulley attached to the ceiling, and we have one rope and a mass M1, and another pulley with mass M2, and let's say M2 is heavier than M1, then M1 would accelerate downwards with acceleration A2, and the M1 would accelerate upwards with acceleration A1. But of course, A1 must equal to A2. Of course, oh, right, they're opposite direction. Yes, they're opposite in direction, but the modulus is the same. The magnitude of that acceleration is the same. But also not just acceleration, but if acceleration is the same, that means the velocity is the same at any point. V1 is V2. And if velocity is the same and time is the same, of course, the displacement S1, not position, but displacement S1 must equal to S2. So if one mass moves 2 meters up, the other one moves 2 meters down. It doesn't always have to be 1-to-1 ratio, so the constraint could be different. So if you have a movable pulley, so for example, if this is the ceiling and there is a movable pulley system like this, so there's a pulley here which is attached to the ceiling, and there's a pulley here attached to a mass M1. And there's a pulley here attached to a mass M2. Now let's say that, well, it is for simplicity, let's say M2 is greater than M1. Yeah. So that means M1 would definitely accelerate downwards, A2, and M1 would accelerate upwards. But the thing is, if you think about it, if the block M2 moves down by a distance x, that means you need an x meters of rope. So you're using x meters of rope. But the other mass is attached to two pieces of rope. So this rope uses x over 2 and x over 2, x over 2 and x over 2. So as M2 moves x down, a distance x down, m1 moves x over 2 up. The link is this. And I hope that makes sense. Intuitively, you kind of can figure it out. Like, yes, if this one moves down, so you've used an X meters of rope. So the rope moves by X meters down. But because this piece is connected to two ropes, then you only need X over 2 twice. And that means that we will only move X over 2. I don't know. I don't know if that's intuitively A1 is not A2. As a matter of fact, A2 is going to be double A1 in this scenario, and that is also a constraint. Constraint. It's just not a not an not a not a 1-to-1 ratio. The ratio is 2-to-1. That happens. So yeah. And you can easily prove that. That means S1 is half of S2. So the distance traveled by the first mass is half the distance traveled by the second mass. And if you differentiate that, you get V1 equal to a half of V2. And if you differentiate that, you get acceleration 1 is half of acceleration 2. We know the velocity is the derivative of displacement, and acceleration is the derivative of velocity. So S1 equals to 1/2 S2. So V1, if you differentiate, V1 equals 1/2 V2, and acceleration is 1/2 A2. Okay, I hope that makes sense. A pulley is designed to increase the force. Okay. And there are different ways you can calculate those forces. Let's leave this to the end, and let's move on to this block. So, what force is required to lift 100 kilograms in each system? So, what do we notice here? Well, the first thing that you should notice that this is a single rope. This is a single rope. That means the tension in the rope is the same everywhere. Single rope. Oh, single rope. Tension, same everywhere. But what that means that if there's 100 kilograms of force, that means it's 1,000 newtons. The weight is 1,000 newtons acting down. But what is supporting that weight? Well, actually, it's 4 ropes. 2, 3, 4. So this mass is being supported by 4 ropes. And that means that the tension in the ropes are the same. And that means that 4 tensions, 4 times T, must equal to 1,000 newtons. And that means that the tension in the rope is equal to 250 newtons. And the force that you need to apply here is only 250 newtons. The force is 250 newtons. So that's the force you need to lift 100 kilograms. So it's equivalent to lifting 25 kilos. So it's 4 times less. So this, we say mechanical advantage is 4. Mechanical advantage is 4. Because for every 1 Newton of force that you apply, the machine generates 4 newtons of force. It is like a gear. It's like on your bicycle. Yeah, if you go in first gear, you can easily go up the hill, but you just have to pedal a lot more. So in this scenario, you have less force, but you need to move the rope a lot more. So in order to lift the mass by 1 meter, you'll have to pull out 4 meters of rope because of the mechanical. Well, you win in force, but you lose in distance. Okay. Oh, yeah, generally speaking, you don't consider the weight of the pulley. Yes, we say the pulley is massless. Otherwise, the calculations just become really complicated because if the pulley has mass, that means the wheel has mass. So you not only need a force to move it, but you also need a force to turn it, and that gets really messy. We talk about this in year 13, but yeah, for in non-advanced physics, you would just normally say they're massless. So yes, it's assumed to be negligible. Is the thing above what we did the V and S stand for again? Velocity and displacement. Yes, velocity. V is velocity, S is displacement. Okay. Now, if you look at this rope system, you can you can actually track the rope. It starts here, it goes round here, round here, round here, round here, and then again here. It looks much more complicated, but actually it's the same system. It's the same four ropes supporting the load. So this is tension, 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 tension. There's four ropes holding one mass, and the tension in the rope is the same everywhere because we already know that. So once again, this is 250 newtons. So to lift 100 kilograms, you need only 250 newtons, where you would normally need 1,000 newtons. Okay, let's look at these. So if you have 1,000 newtons everywhere, attached, how much force do you need here? Well, you already know the trick. You just count the ropes. So this mass is being supported by two ropes. That means you need 500 newtons of force here. This mass is being supported by three ropes, so you need 333 newtons. One, two, three, four ropes, so 250 newtons, and 1, 2, 3, 4, 5, so 200 newtons and 167 newtons here. So the more loops you make, the easier it is to lift. And of course, we assume there's no friction and the pulleys are massless because otherwise it just gets more complicated. But yeah. Now this one is tricky because it doesn't have a single rope. It has different ropes. So let's assume that the force here is F. Actually, no. We can start with 1,000. We can start from the back. So the weight is 1,000 newtons, 100 kilograms, 1,000 newtons, and it is being supported by two ropes, 1 and 2. That means that the tension in each rope is 500. 500 here, 500 here. Now this pulley is being pulled up by two ropes, but being pulled down by this rope, which is 500. So this must be 250 and 250. Same again, this is 250 being pulled down by this rope and being pulled up 125 and 125. And once again, this is being pulled 125, so that's 62.5 and 62.5. And because along this rope, the tension is the same, so this force is also 62.5 newtons. Is it? 62.5 times equals times 2. Yeah. All right. Just 2.5. Feels weird that 1,000 divides by 62 and a half. I don't know. Maybe it's just me. But yeah, that's the idea. As long these are different ropes, so the tension in those ropes are different. So you can't just count the number of ropes. It doesn't work like that. But for each rope, you can do a separate calculation. And I hope that this makes it more intuitive. All right, so let's get to grips with some problems. Accelerating lift with counterweight. A lift of mass m is connected over a frictionless pulley to a counterweight of mass m by the acceleration of the system and the tension in the rope. So that's a very classical problem. So there's a pulley, there's a lift, and there's a counterweight. So mass m, and the counterweight is mass m. There's no friction in the pulley. And we assume it's a stationary pulley, so it's attached to the ceiling. And we just let go, which hopefully never happens in real life. You don't allow lifts just to go on their go accelerating without any friction or any safety mechanisms. But anyways, assuming it just doesn't matter which one, but assume this one's greater. So in these problems, it is very important to follow like a set algorithm, if you wish, because otherwise it gets really confusing. So the algorithm is draw each body separately. Draw each object separately. First, draw each body separately. 2, draw forces on each object. And 3, write Newton's second law for each object. All right, so you start by drawing the first mass. Okay, each object with mass. With with mass. If it doesn't have mass, it doesn't really make sense to write down Newton's second law, because m is 0 and ma is 0. Brackets and apostrophes. What brackets? Oh, the brackets derivatives. So if you're not familiar with calculus, don't worry about it. You'll do calculus next year. So these are derivatives. But do look them up if you are keen. So we start by looking at mass m1. No, oh sorry, m. Because we assume that m1, so it's going to be accelerating downwards. Right? So it's accelerating downwards. And acceleration would, let's call it A. Well, A. Why not? Why not just call it A? And we know there are two forces acting. There's the tension of the rope, which is pulling it up. And there's the gravity pulling it down. And the gravity is mg. Now we can write down Newton's second law. Mass acceleration is equal to the sum of forces. Now it is accelerating downwards, and the mass is m. So big M times acceleration is equal to the forces pulling you down, forces helping you, which is mg, minus the forces preventing you from accelerating, which is T. And that's Newton's second law for the first mass. And we just write it down. Now for the second mass, small m, now it's going to be accelerating upwards. But because of the constraint, it won't be accelerating upwards. And there's a tension in the rope pulling it up, and the gravity pulling it down, mg. And the Newton's second law for this mass is mass times acceleration is equal to the sum of the forces. So forces pulling you forwards minus the forces pulling you back. So tension minus mg. And that's the second equation. We've got two equations. And how many unknowns do we have? Well, two. Unknowns, T is unknown and A is unknown. So therefore we can solve them. So we're going to add the first equation plus the second equation. And we get MA plus M small a equal to mg plus T minus mg. T cancels, and we get acceleration, open bracket, m plus m equals g, open bracket, m minus m. So acceleration is m minus m divided by m plus mg. That's the acceleration of the lift. So this is how physics is done properly, right? So you don't need any numbers. You could have numbers like if m is I don't know 200 kilograms and the counterweight is 150 kilograms, you could easily calculate the acceleration, right? Example, if the acceleration would be 50 divided by 350 times g, so which is approximately 1/7 of g. What's 1/7 of g? 1.2? Is it 2? 9.8 divided by 2? No, divided by 7. 1.4. 1.4 meters per second squared. Right. That's you could calculate acceleration. But this is the answer. So, and then tension. Well, you can work out tension from any of the equations. So you get from equation number 2, we get tension is ma minus mg plus mg, sorry, and that is m multiplied by m minus m over m plus mg minus plus mg, and that is mg, open bracket, m minus m plus m plus m over m plus m. So T is 2m divided by m plus m times mg, or simply 2m mg divided by m plus m. I hope I didn't make a mistake. And this is sort of a standard result. All we can do for this same example, T is ma plus mg, and that is 150 times 1.4 plus 9.8. 150 times 1 times 1.4 plus 9.8. 1,680 newtons. And if we have tension using that formula, is 2 times 200 times 150 times 9.8 divided by 350. Let's see if we get the same result. 2 times 200 times 150 times 9.8 divided by 350. 1000, yeah, 680. Okay, so it looks like I haven't made a mistake, which is great. Okay, so that's. Oh, so let's just move the questions down. Okay, block on a table with a hanging mass. So we have a table, a smooth table, and a pulley, and we have a mass M1 and a rope and a mass M2. And we want to find the acceleration and the tension. Now, the top block will be accelerating to the right. This one will be accelerating downwards. And we draw the first block. The first block, yes, M1. So it's being pulled by tension. It's being pulled back. Oh, it's not being pulled back by anything because it's a smooth table. And there's a normal reaction force and the gravitational force M1G. But these cancel each other out and cancels out this. So if it's accelerating to the right, we can write Newton's second law. Newton's second law is that mass M1 times acceleration is equal to the total force, and the total force is T, because that's the only force accelerating it. Now for the second block, M2. Now it's gravity pulling it down. M2G pulling it down. And there's the tension in the string pulling it up. And it's the same rope, so the tension is the same. And it's accelerating downwards. So Newton's second law is M2 times A is equal to M2G minus tension. So we've got two equations, and now we can add them up. So this is equation number 1, equation number 2, equation 1 plus equation 2, and we get M1A plus M2A. So we've added the left-hand sides, and now I'm adding the right-hand sides, T plus M2G minus T, T cancels, and we get acceleration, open bracket, M1 plus M2 equals M2G. Acceleration is M2G divided by M1 plus M2. So if you think about it, this is quite a nice result. So M2 over M1 plus M2, that's kind of the fraction of the total mass. Fraction of total mass. M2 over M1 plus M2, right? It's what fraction of the mass belongs to M2, because gravity is only accelerating M2. Gravity has no effect on M1. So M1 is only being accelerated by the rope, and the rope is being pulled by gravity. So gravity is accelerating both of them. So it's a fraction of the total mass multiplied by g, which makes perfect sense, if you ask me. And the tension in the rope, of course, you just substitute. T is M1A, and that's M1, M2 over M1 plus M2 times G. Another beautiful result. I think this is called average harmonic. Our average harmonic. Average harmonic average. Harmonic mean. Yeah, I believe so. Harmonic mean of two values. All right, moving on. inclined plane. A mass m1 rests on a smooth incline angle theta and is connected over a string with a pulley. It doesn't specify which way. But we assume it's this way. There's a pulley. So m1, this is m2. And the incline is theta. The acceleration of the system and the tension in each string. So what's happening with m1? So you draw m1 first, and there is being pulled up by tension. So the tension in the rope is being pulled down by gravity, m1g, and there's a normal reaction force here. Now, if we resolve the forces, well, we need to break down mg to components. Oh, too long. So this would be theta, because the way that is. And then this would be m1g cos theta. And this would be m1g sine theta. And it's accelerating up the slope. Well, we assume it's accelerating up the slope. We don't really know, but it doesn't really matter. We can assume that m2 is greater than m1. m2 is greater than m1, so it's actually m2 is greater than m1 tan theta, but it doesn't matter. I think it's m1 tan theta, but so the acceleration is a. So now we can write down Newton's second law. So m1a is equal to the tension minus m1g sine theta. So it's the forces helping you up the slope minus the forces pulling you down. If you actually pull this, would the hooks not make it impractical? Maybe. I'm not sure. I very rarely use pulleys myself. Mostly in science museums. You know, if you go to any science museum, you always have a pulley and you can experiment with a pulley. And for M2 is being pulled down by gravity, so it's M2G. And up is a tension in the rope. It's accelerating downwards, and the acceleration is the same because they're connected by the same string. So the acceleration is downwards. And we can say, okay, so M2G, so M2A is equal to M2G minus the tension. And then that's the first equation, that's the second equation. So we add them plus 2. And we get the first equation plus the second. So we get m1a plus m2a equals t minus m1g sine theta plus m2g minus t. T cancels conveniently. And we have acceleration m1 plus m2 equals g, open bracket, m1 sine m2 minus m1 sine theta. So acceleration is m2 minus m1 sine theta divided by m1 plus m2. Once again, it is a fraction of the total mass. It's a fraction of the total mass multiplied by g, which is and also if m1 if m2 is less than m1 sine theta, right, then acceleration is going to be negative. So it means it's just going to go backwards. So the equation still makes sense, even if we don't assume that M2 is heavier. Tension. The tension in the string, we just use any of the equations. I suppose we use the second equation from 2. We get tension is equal to M2G minus M2A, right? And oh, I think I made a mistake here. To T's MA. Oh no, I haven't. Okay, no, that's fine. T is M2G minus M2A. Mm-hmm. And so we just substitute that in. So it's M2G minus M2 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 minus M1 sine theta divided by M1 plus M2 G. Um, I'll just leave it like this. I don't want to mess it up, honestly. So yeah, that's the answer. That's the answer. This one and this one. All right, moving on. Problem 4. Moving pulley, lifting a movable pulley, lifting a load. A mass M is attached to a movable pulley. The rope is pulled with force F. An acceleration of. Oh, that's boring. I'm gonna make it more interesting. I'm gonna make it more interesting. A mass is attached to a movable. The rope, another mass M. Another mass M is attached. By the acceleration of the load, tension in the rope. So what do we mean by that? Well, if this is the ceiling, then this is a stationary pulley. Stationary. And then this is a movable pulley. So mass M, big M, is attached to a movable pulley. And there is a small mass attached to the rope. Right. So now we do have a constraint. So let's say that this one is accelerating downwards with acceleration A1, and this one is accelerating upwards with acceleration A2. But we already know that they have different accelerations because they're attached to the same rope, but this is attached to the same rope twice. So in order to move 1 meter, each rope has to, so the rope has to shrink by 2 meters, if that makes sense. So if we pull the rope by 1 meter, the total, this thing moves by 2 meters. And another way of looking at it is if we look at this section here, we move at this section here. Like if we pull the rope up, if if we pull the B up by a distance x, then an A stays stationary, then the midpoint moves up only by x over 2. So if you think about, so x is the point A is stationary, but point B moves up. So if if this is my movable pulley here, and this is the rope, so if I pull the rope by 10 centimeters up, the midpoint only raises by 5 centimeters. So that's the idea of a movable pulley. It's the same as a lever. So if you move this end of the lever by 10 centimeters, this only raises by 5. So hopefully that makes sense. So the constraint is A2 is half of A1. And then we can, well, we can do the same thing. So, or starting with a small block, a small mass, M, and it's M, mg, and there's the tension. And for the other block, so we have M, big M. So it's being pulled up by two ropes, T and T, and it's being pulled down by gravity, mg. And this one is accelerating downwards with acceleration a1, and this is accelerating upwards with acceleration a2. So ma1 is equal to mg minus t. That's the first equation. And for this one, it's accelerating up. So big M, A2, mass times acceleration, is the forces that are helping you up. So 2t minus mg. Okay, so, and remember that A1 is half of A2 is half of A1. A1 is 2A2. So we can, so 2MA2 equals mg minus t. And here we have MA2 equals 2t minus mg. Let's multiply this by 2. So we get 4ma2 equals 2mg minus 2t. And then we add the two equations and we get ma2 plus 4ma2 equals 2mg minus mg. A2, open bracket, m plus 4m equals 2m minus mg. So A2 is 2m minus m plus 4mg. Beautiful. This is A2, and A1 is simply double that. So it's 4m minus 2m divided by m plus 4mg. As you can see, once again, acceleration is a fraction of g, and that fraction depends on the mass distribution. And look, if, in this case, if, looking at this fraction, this value can sometimes be negative. If m is greater than 2m, if the ratio is that, then A2 is going to be negative because this is going to be a negative value. And then it just means that the blocks will move in the reverse direction. The blocks move in reverse direction. Not the one that we assumed, right? You don't always know which way they're going to move, but once you've calculated it, you can tell the conditions. Well, if the mass of if the big block is more than double the mass, so if if m is more than 2m, big block moves down. M moves down. And if m is less than 2m, so m moves up. And if m equals to m, then it's equilibrium. And so equilibrium. Is it one single L? Oh, come on. Me and spelling. Equilibrium. Equilibrium. No, single L. Right. Equilibrium, so it means stationary or moves at constant speed. So it can in either direction, right? If they are the same, they can either move up or can move down. If there's no friction, they can you just push it and it just goes, or you push it down, it goes. Right. Okay, that was a nice question. I've modified it to make it more interesting. Okay. Moving on. Okay, just move some space. Two blocks on the table with friction. Two blocks are on a horizontal table. So we have M1 and M2. They are connected by a pulley. The coefficient between friction between the blocks on the table is mu. So mu. The pulley is pulled with force F. So the pulley is pulled with force F. Find the acceleration and the tension in the rope. Right. So in this case, we have to, and the mass of the pulley is 0. We have to say that the mass of the pulley is 0. Let's call it M pulley, MP0. So we start with the top block. The top block is M1. So it has a friction force backwards, which is mu times N. And there's a tension force pulling it forward. So there's tension pulling it forward and the friction pulling it backwards. And the friction, because we assume that it's going to slide, it's going to be mu N and M2 also T and mu N2, mu N1. But N1, because it's on the table, N1 is M1G and N2 is M2G. And they're both accelerating. One is accelerating at acceleration A1, the other one is accelerating at A2. So we can write down Newton's second law. Mass 1 times acceleration 1 is equal to T minus mu M1G. For the second block, M2A2 is equal to T minus mu. It's the same rope, so it's the same tension in 2G. Same rope, so it's the same tension everywhere. And then for the pulley, for the pulley itself, Now this is quite an unusual because the mass of the pulley is 0, but we still want to write down the force of pull is that, and there's two tensions, T and T. So mass acceleration is equal to mass of the pulley times acceleration is the force minus T minus T. But we know that MP0, so that 0 equals F minus 2T. So F must equal to 2T. That's another important. Right, so we can just add them. Do we want to add them? Or what do you want to find? That depends. The tension. Well, the tension is just simply F over 2. That's easy. The acceleration. Well, acceleration is this. So let's take one of them. A1. So from the first equation, of course. A1 is T minus mu M1G divided by M1. So that is equal to F over 2. So F over 2M1 minus mu G. That's the acceleration of the first block. For the second block, A2 is F over 2M2, of course, and minus mu G. Oh, nice. So we found the accelerations. What else do we need? Oh, the length of the rope on either side is L1 and L2. Well, if this is L1 and this is L2, so if M1 is going to be bigger, yeah, so they have different accelerations, and that's normal. Even though they're connected by a rope, that's a good point. Thank you. That's for that question. Look, I'll try to do an experiment. What can I do? Oh, I can use two phones. Sorry for the mess. So this is my experimental setup. I've got one phone. I've got another phone. So this is my M1 and M2. They probably have different mass. Okay, and now right here I have my pulley. So this blue ball is going to be my pulley. So if I pull the pulley, you can see that the phones accelerate, yet acceleration might be different. Like okay, I'm not very good at this, but maybe this is better. Oh, they're quite even. So what if I make one significantly heavier? Oh wow, they're still accelerating at almost the same rate. Uh, oh yes, here it is. You can see that even though the lighter phone moves much faster than the heavier one, they both move in the same direction. Does that answer your question? Because I'm pulling the block. Right, so it's this situation, right? It could be that one of them is actually stationary. So it definitely could be. All right. Cool. So okay. Uh, right. So I'm pulling on the pulley, and both masses I'm pulled to the right because the tension, the rope cannot pull you to the left by any means. So they both accelerate to the right. Acceleration is going to be different, and yeah, and of course, oh, you can write the condition for movement if F over 2m 1 is less than mu g, then A1 will be stationary. A1 will be stationary. M1 will be stationary. Stationary. just like I've demonstrated. Mu is the coefficient of friction. Mu is the coefficient of friction with the ground. Right. Anyways, the length of the rope. So if the length of the rope is L1, so assume L1 M1 is heavier than M2. That means hence A1 would be less than A2. Um, sorry, it's gonna get really messy. I apologize. Let's just not do the last question. It's it's um it's homework. I'll leave it to you as homework. It's unnecessarily complicated at the moment. Right. Do try to figure it out because I've got two exciting questions coming up and I really want to focus on them. So this is an A-level question. Two particles of P and Q have mass 0.5 and 0.4 kilograms respectively. Particles are attached to the ends of a light inextensible string. The strings are passed over a smooth pulley, which is fixed above a horizontal floor. Both particles are held with the string taut at a height of 2 meters above the floor. The particles are released from rest in subsequent motion. Q does not reach the pulley. All right, so P is heavier, so it accelerates down, and Q accelerates up with acceleration A. So for P, we can write down mg, mpg, and tension. And for Q, we can write m2g and tension. And P is accelerating down, and Q is accelerating up. So MPA equals MPG minus T. And here MQ A equals T minus MQG. P is heavier, so Q will go down, Q will go up. Q, as in P goes down, but Q goes up, but Q doesn't reach the pulley. It doesn't hit the pulley. That's what they're trying to say. Right. I really don't like MP and MQ. I'm gonna change it to M1 and M2. M1 and M2G. M1, M1, M2, M2. And we're done the equation of motion of P, the equation of motion of Q, so I've done that. Find the tension in the string immediately after the particles are released, so we need T. Well, we definitely need to find acceleration first, so we add the two. M1A plus M2A equals M1G minus M2G. So acceleration is M1 minus M2 over M1 plus M2G. And we can calculate that. So M1 minus M2, that's 0.1. M1 plus M2 is 0.9. So that's 1/9 of G. So that's 1/9 G. And then the tension in the string is going to be M1G minus M1A. So M1 is 0.5 times G minus 0.5 times 1/9 G So it's half G times 8/9. So that's 4/9 G newtons, of course. Right, so that's the tension. The particles, when the particles are moving by 0.2 seconds, the string breaks. Find the further time that elapses until Q hits the floor. So after 0.2 seconds, so they've been accelerating for 0.2 seconds. So Q has been moving up. So Q moves up. So part B, Q moves up with constant acceleration. Acceleration for 0.2 seconds. So it's a suvat. Exciting. We know that. Suvat. So S is question mark. We need to know how far it goes up. U is 0. V is question mark. Acceleration is a 4/9 of G. So 4/9 of G, which is approximately 4/9 times 9.8. 4.36, 4.36, and t is 0.2 seconds. So we can find the final velocity is u plus at. So that's 0 plus 4.36 multiplied by 0.2. Have I 1/9 of g? Oh, what am I saying? No, 1/9 of g. That's tension 4/9. Pause. That doesn't make any sense. 1/9 of g. So it's not 4.36. 9.8 divided by 9. 1.0. 1.1. Acceleration is 1/9 g, which is approximately 1.1 meters per second squared. 1.1 times 0.2. So that's 0.22. 0.22 meters per second. So by the time the string breaks, it reaches 0.22 meters per second. That's the speed. And displacement, now it is, well, we can use 1/2 u plus v over 1/2 u plus v times t. So 1/2 multiplied by 0 plus 0.22 times t, 0.2. So times 0.1. That's 0.022 meters. That doesn't. Is it? Oh yeah, 0.2 seconds. You don't fall very far. If the speed is only 0.22 meters per second, yeah. Okay. So basically what happens with Q, so Q is now at a height of not 2 meters, but 2.022 meters. And it is launched upwards at a speed of 0.22 meters per second. So it goes up and then it goes down. And we need to find the time. So this is another suvat. It's a suvat number 2. And S is minus 2.022 meters. U is 0.22. Final velocity is, we don't know. Acceleration is minus 9.8, so it's accelerating down. And t, I'm using minus 9.8 because it's an A-level question. In maths A-level, they ask you to use 9.8. And t is question mark. So we need, well, with no v. So s is equals to ut plus 1/2 at squared. So minus 2.022 equals u, which is 0.22 times t, plus minus 4.9 t squared. So this is a quadratic equation, 4.9 t squared minus 0.22 t minus 2.022, and that's equals to 0. So we solve the quadratic. In this case, this particular case, I'm just using my calculator. So 4.9 minus 0.22 and minus 2.022. And that is 0.665, or the other answer is negative. So T2 is minus 0.620. So that doesn't make any sense. So it takes another 0.665 seconds to hit the floor. So basically, P goes down, Q goes up. Q goes up, it gains speed, but then the string breaks, so it goes up a little bit and then falls back down. And hopefully I haven't made a mistake, but yeah, it does seem that Q moves a very small distance up, only 2 centimeters. It only manages to move 2 centimeters before the string breaks. Unless I've made a terrible mistake somewhere, I don't think I have. 0.2 seconds, acceleration 1.1. Yeah, I think it looks realistic. If you find a mistake, please let me know. And final question. Oh, what did I lose? So this is an Isaac Physics question. Isaac Physics is a wonderful website for physics. Okay, so particle P of mass 0.4 kilograms. 4 kilograms. The attached to one end of the light inextensible string. The string is passed over a smooth pulley, and particle Q of mass 0.1 kilograms is attached to the other end. P rests in limiting equilibrium on the horizontal surface, which is 0.4 meters below the pulley, which the string taut and the plane. P is 0.5 meters away from the pulley. All right. So we want to know, well, P is in limiting equilibrium. So we start by drawing Q. Q is nice and easy. There's a tension up, and there's MQG. Let's call it M2G. So because acceleration is 0, it's not stationary. That means it's stationary. It means tension in the rope is M2G. And now P. P is a much more complicated story. So P is being pulled up by the string. It is being pulled down by gravity, M1G. There's a normal reaction force, so N1, and there's a friction force. And because it's a limiting equilibrium, that means it's mu N1. Right, mu is the coefficient of friction. Now, horizontal, we can split T into components. T, if this is theta, T cos theta, and T sine theta. So for horizontal forces, T cos theta must equal to mu N1. Vertical, T sine theta plus N1 equals to M1G. So from here, from the second equation, we calculate N1 is M1G minus T sine theta. And we know that T is M2G. So it's M1G minus M2G sine theta. And for sine theta, well, we know that this is theta. This is 0.4 and this is 0.5. So sine theta is 4/5. That makes cos theta 3/5 because of Pythagoras theorem. And therefore, it's equal to m1g minus 0.8 m2g. Lovely. That's the normal reaction force. And t cos theta. So from the first equation, that's from the second equation. From the first equation, we get mu is equal to t cos theta divided by n1. So t cos theta, so that is m2g cos theta times 0.6 divided by, because that's 3/5, divided by n1, so m1g minus 0.8 m2g. G cancels, and we're left with 0.6 m2 divided by m1 minus 0.8 m2. And m2 is 0.1, and this is 0.4. So 0.6 multiplied by 0.1 divided by 0.4 minus 0.08, which is 0.06 divided by 0.32, 3/16. 3/16, so which is 0.1875. That's the coefficient of friction. Contact force. For calculate magnitude exerted on P by the surface, from the surface. So that's N1. 0.1875. And that's mu. Coefficient of friction is mu. N1, that's the normal force. And N1, we know that's M1G minus 0.8 M2G. Ooh, I think we've already done that. So that's 0.4. So that's 0.32 times G times 10. So that's 3.2. 3.2 newtons. Acceleration of particles. Q1 is now moved to the position on the surface below the pulley, such that the portion of the string attached to Q is vertical. P hangs freely below the pulley. Right, so we have a situation here. So Q is here, P is here, and the pulley is here. And now we need to find the acceleration. Well, we already know the formula actually. So it's m1 minus m2 divided by m1 plus m2 times g. So m1, so 0.4 minus 0.1 divided by 0.5, which is times g, which is 3/5 g. So 0.6 g, which is 6 meters per second squared. Perfect. Oh, that was easy. Now, find the tension in the string while it is descending. Well, you already know that too, because we've done this question before. So if we look at question P, mass P, so M1G and tension, and we know that it's accelerating down and the acceleration is 6 meters per second squared. That means mass acceleration equals M1G minus T. So T is M1 G minus M1A. So that is 0.4 multiplied by 10 minus 0.4 multiplied by 6. So that's 4 minus 2.4, which is 1.6 newtons. That's lovely. P strikes the surface and remains at rest. Q comes into instantaneous rest immediately before reaching the pulley. Find the length of the string to two significant figures. All right. So when P hits the ground, Q is moving up. Q is moving up with some speed. And it stops just before reaching the pulley. And we remember that the total distance is 0.4 meters. 0.4 meters. Right, so let's say it moved up by X meters, and then it traveled X meters, and then it traveled Y meters. Well, not Y, but 0.4 minus X. So stage one, Q is accelerating, rating. And stage two, rope is slack and Q is decelerating, rating. Right, so you understand what's going on. So Q is attached to a rope. So it first is accelerating up, but then E hits the ground and the rope is slack. And then Q is now slowing down because there's nothing pulling it up. Rope is slack. All right, so stage one of motion of Q. It's a suvat. Displacement is x, which we don't know. Initial velocity is 0. Final velocity is we don't know. And acceleration is, we do know the acceleration. The acceleration is 6 meters per second squared. 6 meters per second squared. And t is, I don't think we need t. Yeah, we definitely don't need t. So we need equation without t. So v squared equals u squared plus 2as. So v squared is equal to 0 squared plus 2 times 6 times x. And so v is square root of 12x. Oh, nice. Stage two. So in stage two, now the Q is moving up with initial velocity root 12x, and then it's traveling up and then stopping just before reaching the pulley. So we write another suvat. Displacement is 0.4 minus x. Initial velocity is square root of 12x. Final velocity is 0. Acceleration is minus 10 because it's now doing freely under gravity, moving freely under gravity, and we don't care about t. So we write down the same equation, v squared equals u squared plus 2as. V is 0 equals 12x minus 20 times s, 0.4 minus x. Looks like we have, do we have a quadratic? No, we don't even have a quadratic. It's just lovely. So 12x minus 20, so minus 8 plus 20x equals 0. So 32x equals 8, x equals 0.25 meters. Right. So it's moved up by 0.25 meters when, by the time the Q, when P hit the ground, the Q was 0.25 meters above the ground, 5 meters. This is 0.4 meters. So this must be 0.4 minus 0.4. So this is 0.15 meters. So total length of the rope, is 0.4 plus 0.15 meters. I love this question. This is so, I think it's the best question I've seen on Isaac Physics. 0.55 meters. Just the last part, like the first part was quite basic, but this is indeed a very nice one. Lovely. I think I'll leave you here. Hope that was useful. Oh, there's another question. The ball is moving up. How is the acceleration minus 10? No, so first is accelerating up, so it's positive acceleration, and then it's slowing down, so slow down, so it's negative acceleration. No, that makes perfect sense. If you're moving up is positive, so I chose up to be positive, so it's accelerating up, and then it started to decelerate, and it stopped at the top. So it's slowing down, so it's moving up but decelerating. That's what it means. Okay, I'll see you all. When do I see you? I think it's let's check. 9th of March. Oh yeah, that makes perfect sense. Okay, so we'll do simultaneous equations. I'll see you all, and bye.